Good morning, everybody.
Good morning.
Good morning, ma'am. Good morning, sir.
Can you hear me?
Yes,
Ma'am.
ma'am.
Yes, we can hear you.
Yes, ma'am.
Saujanya, we can hear you.
Okay. Good morning, everybody. To today's webinar on persistent memory. I welcome Professor S. Vijayanand Rao Garu, Head of the Department ITCA, Professor Kunjam Nageshwar Rao Garu, Head of the Department CSSC, our speaker today, Dr. Praveen Kumar, all the faculty members, scholars, and participants. I request Professor Shashi Madam to take over.
Yeah, I'm happy to provide or coordinate a webinar by one of our brilliant students of this department, Dr. Praveen Kumar Edlapalli. He finished his BTech during 2002 to 6 from this department, BTech Computer Science. And then he proceeded for his MTech CSE in IIT Kanpur. And then finally, he joined Penn State University in USA for his PhD and finished his PhD under a very highly reputed guide. His name is, what is the name of your guide, Praveen?
Kandemir.
Yeah, Condiment. So he did a very excellent work on computer architectures, especially the multi-core architectures, which are the trend of that particular time during 2008 and 2014. And finally, while doing his PhD, he could achieve patents as he worked for his internship in VMware. And the VMware company liked him so much that they offered a permanent job there itself. And he is working in that VMware from then onwards. So his research interest for the present is designing efficient compilers that leverages the potential of multi-core architectures and the other aspects which are towards, that means how to make use of the hardware support in order to achieve better performance on computer systems. So nowadays, the persistent memories is one of the very useful development in computer architectures. And today's lecture, Praveen will be enlightening us on that particular aspect. Actually, I was expecting that Mary Saujanya will be providing you the basic details of Praveen Kumar, but somehow there is a slight confusion. And no problem, because I know Praveen Kumar very well. I can introduce without any paper preparation. And another thing that I am very, I profoundly recollect is that he shared his knowledge on these multi-core architectures 4 or 5 years back when I was head of the department we have arranged one talk during his visit to India on multi-core architectures. And I remember the very highly informative lecture he has provided during that particular talk. That is why I was interested, and I was insisting that he should share his knowledge to the students of this department on the latest aspect of computer architecture, that is persistent memories. So actually, I thank the head of the department of CSE, Kunja Nageshwarrao Garu, and head of the department of IT department, IT, Vijayanand Garu, and then our principal for encouraging me in arranging this particular lecture. Our principal, Peri Srinivas Rao Garu, is not available today because of some other assignment. So today, actually, the principal is the registrar of Andra University, in charge principal, Professor Krishna Mohan Garu. And with the support of our Vice Chancellor and encouragement of our authorities, AU authorities, like Vice Chancellor Professor PVJD Prasad Reddy Garu, and Rector Madam Samata, and our principal and registrar Krishna Mohan Garu, we could arrange such webinars every week or now and then in this department, so that you can get additional knowledge beyond the curriculum. Okay, so make use of this wonderful opportunity to enhance your knowledge beyond your just formal curriculum. Okay, thank you, one and all. I request the resource person of today's webinar, Dr. Praveen Kumar Edlapalli, to share your knowledge to all of us.
Thank you, Professor Shashi Garu.
Just wait. Sorry, Praveen. Before actual starting, let us have our head of the department, Professor Kunja Nageshwarrao Garu, to share his inputs to us just before starting.
Good morning, all the participants, and good evening to Praveen, Dr. Praveen Garu.
It's muted, Andy.
Good evening, Praveen Garu, and welcome to the webinar on persistent memory. Thank you for accepting our invitation. So thank you all the authorities, like principal and registrar of Andra University, the coordinator, today's webinar, Professor Shashi Madam, and all the colleagues. Thank you for accepting, and we need your cooperation for the future programs also, sir. Thank you, Praveen Garu. Thank you all. The madam will continue this program.
Yeah, thank you, everyone.
Dr. Praveen Kumar Garu to start the session. Thank you.
Okay. Thank you, everyone, for the opportunity. This is a very good chance for me to show my work and give some knowledge to you guys. Thank you. Let me start. So I'm Praveen. I work at VMware. Today I'm here to talk about this new technology called persistent memory. Okay. Before understanding what persistent memory is, first we need to understand what is the difference between memory and storage. Okay, let's say you are trying to buy a laptop. And what are the main things that you look for in a laptop? First thing is the CPU. How fast is the CPU? Next is memory. How many GBs of memory does it have? And the other thing is storage. How much hard disk or SSD does it have? In this example, I'm showing a 16 GB memory and 512 GB SSD in this particular laptop. So what exactly is the difference between this 16 GB memory and 512 GB SSD? Let's understand that. So all the processing in a computer happens in the CPU, but all the data in the computer resides either in memory or storage. So here I am showing the difference between memory in the green and storage in dark blue. So the main difference is to access memory, you do load store instructions, CPU instructions. But to access storage, you do a different kind of operation called block store, like read and write operations. That's the main difference. And the other difference is in memory, latency is very low. That means it's very fast in the order of nanoseconds. And storage is long latency in the order of microseconds. But the main advantage of this storage is non-volatile. That means when you switch off the computer and you power it on again tomorrow, let's say, next day, you still have all the data that you store in the hard disk or storage. But whatever was in memory, it's gone. Once you power off the system, the memory is all cleared. It's all zero. Okay, that's the main advantage of storage. It's non-volatile. That means it's persistent. So as you go up this pyramid, going from magnetic hard disk to SSD to DRAM to cache, the speed is increasing. As you go higher, it's faster, very, very fast. But as you go lower, you can get much bigger size device. Like you can get a 512 GB SSD. In the laptop that I showed previously, it has 512 GB SSD, but you can't get 512 GB memory in that laptop. It's not possible. Memory is limited to 16 GB, maybe 32 GB. That's the max in a laptop. But SSDs, you can get 512 GB or even 1 terabyte in a laptop. So the advantage of this storage is you can have big capacity compared to memory. That's the other advantage. The first advantage of storage is non-volatile, and the second advantage is capacity. But the good thing about memory is it's very fast. In nanoseconds, you can read the data from memory. Okay, that's the main difference between memory and storage. So how does this memory and storage sit in a system? Like on the motherboard, there is a place for CPU and there is a place for DRAM DIMMs. You can insert DIMMs there are slots already, and you can insert DRAM DIMMs into those slots. So between the CPU and DRAM, there is a very high speed bus called membus. And similarly, there is a place on the motherboard to insert this SSD, and that is connected to the CPU through PCIe bus. The main difference between these two is PCIe bus is much slower compared to memory bus. See here, you can get 80 Gbps on the memory bus, but on the PCIe bus, it's only 4 Gbps. And also the latency is like 100 times slower on the PCIe bus. So instead of 0.1 microseconds, any read or write will take 10 microseconds. That's like 100 times slower. So that's how the DRAM and SSD sit in a system, motherboard. And that's the speed difference between them. So the main problem now is for the last few decades, CPU speed has been increasing exponentially. Every generation, the speed is becoming double, and it's increasing exponentially. And if you compare that to the storage speed, it's lagging behind. You can see from 2005 to 2013, there is only slight change in storage speed. So this difference in performance between CPU and storage is causing a lot of performance problems for many applications, like even like big applications like Instagram or TikTok or Facebook. All of these depend on both CPU and storage. Everything should run very fast so that we can get all these applications running faster, like Google search. If you want it to be fast, everything on the system should be fast, like CPU should be fast, memory should be fast, storage should be fast. If only CPU is the only thing that is fast, that's not enough for any application that depends on all components of the system. So the solution for this problem, this performance gap between CPU and hard disk, is the topic of today's talk, which is, again, I'm showing this pyramid. There is this new technology called persistent memory, which is a combination of memory and storage. So it takes the good thing about memory, which is low latency and load store semantics. It also has the good thing about storage, which is non-volatile. So that's why it is called persistent memory. And the other advantage of storage is high capacity, like I said. And persistent memory also has that high capacity advantage. So it takes both good things from memory and good things from storage, and this is built into one new technology called persistent memory. Okay. If you have any questions, you can ask in the middle also, that's fine. So now that we have this new PMEM DIMM that comes like a DRAM DIMM, looks like a DRAM DIMM. You can see the picture here, it's in blue in color, PMEM DIMM. So again, this PMEM DIMM sits on the same bus as the memory DRAM. So it has this advantage of 80 Gbps memory bus. Compare that to SSD, which is limited to 4 Gbps. So this PMEM can take advantage of this new existing memory bus, which can be very fast and very low latency. So this persistent memory, there are two different types of persistent memory. One is called NVDIMM-F, which is actually a DIMM. DIMM means this you can see in the picture, right? The green one, that's a DIMM, or the blue one, that's a DIMM. There is a slot on the motherboard, you can insert this DIMM. Okay, so NVDIMM-F or N, what it does is, on the DIMM itself, there is both DRAM chip and a storage chip. So it has some internal firmware which will move the data from DRAM to storage, and it has some complicated algorithm to do that. So every time there is a power off from the DRAM, it moves all the data to the storage. And when you power it on the system, when you power on the system back, it brings all the data from storage, the flash storage, onto DRAM location. So it looks like when you power off and power on, you still have all the data that you put on the DIMM because of this flash storage. The solution is expensive because on the single DIMM, there is this DRAM portion and there is a storage portion. And it's a little complicated with all the algorithm and extra processing and all that on the chip. And also the other problem with this NVDIMM-F is limited size. You can get only up to 128 GB DIMMs. But the good thing about this NVDIMM-F is it's very fast, just like DRAM. It's the same speed as DRAM because it's actually DRAM on the chip. Both HP and Dell are selling this kind of NVDIMMs. The other type of NVDIMM is called NVDIMM-P, which is totally new non-volatile technology DIMM. That means there is no DRAM, there is no storage on the DIMM. It's a new type of material on the DIMM. So it has this property of persistence. So even when you power off, it will remember all the data, just like storage SSD. It won't lose all the data like DRAM. So compared to DRAM, it is cheaper, and you can get up to 512 GB DIMMs. Instead of, like the previous solution was only up to 128 GB DIMMs, but this one can go up to 512 GB DIMMs. So if a processor has 4 DIMM slots, you can have up to 4 PMEM, and it can be like 2 terabytes of PMEM on the system. One slight problem with this NVDIMM-P is it's not as fast as DRAM, but still it's much better than storage. And Intel sells this DIMM. It's called Intel Optane memory. You can buy that for much cheaper price compared to DRAM. So if you want to buy 128 GB DRAM DIMMs, let's say it's $400. This 512 GB DIMM is only like $600. So it's 4 times the capacity, but only 1.5 times the price. That's the main advantage of this NVDIMM-P. So going forward, I'm going to focus on this Intel solution because that's more scalable and more advantageous solution NVDIMM-P, which is Intel Optane. Okay, now that we understand what persistent memory is, let's go ahead and focus on how to use this persistent memory in your software and how your application can become faster using this persistent memory. Okay, first there are different modes in which you can use this persistent memory. Let's talk about them. The first one is you can configure in the BIOS. When you reboot, you can go into BIOS. If you have a system with persistent memory hardware on the motherboard, you can go into BIOS and you can configure 2 different modes. First mode is called memory mode. In this mode, the hardware exposes this PMEM as a full system memory. Okay, operating system or so any software doesn't see that there is a DRAM. So the DRAM is used as cache by the hardware. Okay, let me tell you with an example that will make it clear. So let's say a system has 16 GB DRAM and 128 GB PMEM. Both of these DIMMs are inserted in the motherboard. So if you configure memory mode, the OS, either Windows or Linux, it sees 128 GB as the system memory. Full PMEM is system memory. The 16 GB DRAM is used as cache for this 128 GB PMEM. So hardware manages this cache, so it will move the data between DRAM and PMEM. It identifies what is important and puts it into DRAM, and remaining will be in PMEM. But main point about this memory mode is operating system or software doesn't know that there is this DRAM, PMEM, and all of this in the hardware. It only sees this 128 GB as system memory. It can use all 128 GB as memory. The advantage of this mode is easy adoption. So because software doesn't need to understand any PMEM or anything, so you just run any software and it just takes advantage of this large system memory. You insert a PMEM and all of that looks like a large DRAM for much cheaper price. The disadvantage here is this solution is only taking advantage of the capacity and speed of PMEM, but actually PMEM is persistent. But in memory mode, when you reboot, the hardware will remove everything from the PMEM. Even though it is actually persistent, it will intentionally delete everything from the PMEM so that next time you boot, the system memory is clear. That is memory mode. The other mode is called app direct mode. In this mode, you go into the BIOS and change this PMEM mode into app direct from memory mode. You can change in the BIOS when you reboot. So in the app direct mode, the PMEM is used as a fast storage, and the DRAM on the system is regular system memory. So in this mode, it is software managed. So the operating system needs to understand that there is a new device, PMM device, and it needs the device driver for that device. So the same example, let's say a system has 16 GB DRAM and 128 GB PMM. If you configure app direct mode, OS sees 16 GB as system memory. OS also sees 128 GB as a storage device. It looks like a new hard disk. Okay. So the advantage of this app direct mode is now we are taking advantage of the capacity, speed, and persistence of PMM. So anything that you write into this 128 GB storage device, that is persistent. That means if you power off and power on the system, next day you still have all the data on the PMM. The disadvantage is only newer operating systems understand this, has this PMM driver. So if you want Windows 2012, app direct mode doesn't work on Windows 2012 because Windows 2012 doesn't understand PMM device. But you can configure memory mode, and any old, even Windows XP, which is 20 years old, can work. You take advantage of this memory mode. So app direct mode needs newer, like something like Windows 2018 can work fine with app direct mode. It has the driver for persistent memory, so it'll understand there is a separate device, 128 GB storage device, and it can show it to the software. Any questions about memory mode, app direct mode?
Yeah, it's all clear, very clear.
Okay.
I don't think there are any questions.
Okay. So like I said, memory mode, it's all done by the hardware. It's like hardware magic. Operating system or software doesn't see anything. So let me show how app direct mode shows up in the software. So in Linux, when you boot Linux, any Linux, like Ubuntu or something, with a PMM device, it will show up as a block device. Here you can see as a block device /dev/pmm0. It is a block device. And on the block device, you can format with any file system. Here I am formatting with ext4 file system. And once you format the file system, you can mount any folder on that device. And once you mount any folder, you can obviously use it for any workload that you want. If you are running a database or if you're running a game, you can put all your data on that folder, and everything is coming from PMM device. It's writing into PMM, reading from PMM. So all your operations will be very fast, even compared to fast NVMe SSD. It will be much faster. I'll show how much faster it is compared to a fast SSD. So this is Linux. This is how you configure PMM in Linux and use it. Again, in Windows, if you boot Windows with a PMM device, you can see a new disk that shows up, and you can just format it again with NTFS or something and use it for your application. If you want to put some whatever data you want, that needs high speed, like games or database or movies, sometimes processing, you need high speed storage. You can put all of that in this new disk. That's how it shows up in Linux and Windows. So now let's talk about how you can, once you configure it, how you can take advantage of this memory mode. First memory mode, then I'll talk about app direct mode. Okay. So here I'm doing an experiment. I have two systems, one with pure DRAM on the left side. It has Intel processor, 384 GB DRAM, and some SSD, Intel P4800 SSD, and some network card and all that. So the main difference between the DRAM system and PMM system is, instead of 384 GB DRAM, on the PMM system, I have 128 GB DRAM and 512 GB PMM. So both this combination is the same price as buying 384 GB DRAM. So 128 GB DRAM plus 512 GB DRAM, 512 GB PMM cost the same as 384 GB DRAM on the left. So that's why we are comparing these two configurations. Okay. So remember, in the memory mode, the operating system doesn't see PMM. It just sees a large memory. Okay. So on the left side system, you get a 384 GB system memory. On the right side system, if you boot Linux or Windows, you see 512 GB system memory. Although this 512 GB is actually 128 GB DRAM plus 512 GB PMM, which is again managed by the hardware. So this large memory you're getting for same price as 384 GB. So when you run first I'm running a workload called VM Mark, which is like multiple VMs are started on the system, and it will try to run as many VMs as possible. Okay, on the DRAM system, if you can run more VMs, that's better. That's the result of this test. It will show how many VMs it was able to run. On the DRAM system, I am able to run only 6 VMs, virtual machines. VM is like a virtual machine. Each virtual machine is running a application, like simulation application. On the DRAM system, I am able to run only 6 virtual machines, but on the PMM system, which costs the same, I am able to run 8 virtual machines. So that's a 30% increase in my capacity for the same price. That's the advantage of PMM compared to DRAM. The next test is called View Planner VDI, which is like multiple people are logging into the system, Windows system, and opening different applications like PowerPoint, Chrome web browser, and all that. So here I'm showing how many, again, the result here is how many VMs can I run on the system. Higher is better. So if I can run more VMs, that's good for my business. Okay. So on the DRAM system, which is blue line, when I try to run 45 VMs, latency is okay. So any latency that is below this dashed line is acceptable. If the latency is going above this dashed line, that's not good. That means people who are logging in are seeing like slower response time. When you open Chrome, instead of taking 2 seconds, it will take 20 seconds. Or when you try to run a movie or a game, it is taking more. Higher latency, that's bad. So anything above this dashed line is not valid. So on the DRAM system, this blue line, when I try to run 45 VMs, it's okay. It's running below the latency is below the dashed line. But when I try to run 50 VMs, the latency goes up so much and it's not valid. But the green line, which is PMM line, when I try to run 50 VMs, it's below the dash line. Even when I try to run 55 VMs, I'm still below the threshold latency. Only when I try to run 60 VMs, I am crossing this threshold latency of 6 seconds. So that means I am able to run 55 VMs successfully on a PMM system compared to only 45 VMs on DRAM system. That's again showing that my PMM system, which is the same cost as DRAM system, is able to run like 20% more work than DRAM system. That's the advantage of PMM in memory mode. Now let's talk about the other mode, which is App Direct mode, how we can use App Direct mode and what kind of applications can take advantage of this App Direct mode. Again, here I have a HP server, which is like 2 sockets, 2 CPUs with some 256 GB memory and 512 GB PMM. So remember, this is App Direct mode. That means the operating system sees memory separately, 256 GB as DRAM, and it sees the PMM separately as a 512 GB storage device. Okay, that's the App Direct mode. In this App Direct mode, I'm going to talk about 4 different types of applications which can take advantage of this App Direct mode. First one is I'm going to show raw IO performance. What is the best case performance you can get with this PMEM device. Next, I'm going to talk about some relational databases like MySQL, Oracle, which are very widely used databases in different applications. And next, I'm going to show scale-out performance using multiple MySQL databases. And finally, I'm going to show the PMEM-aware applications, which is like application that is modified to understand this new PMEM technology and take advantage of this new PMEM technology. I'm going to talk about SQL Server, which is Microsoft database application, and I'm going to talk about Redis, which is in-memory database. First, let's talk about raw I/O performance with FIO. FIO is a small benchmark that you can configure to run different modes like random read, random write, random read-write combination. Here I'm doing 3 different tests and comparing 4 KB throughput, which is like bandwidth. How much bandwidth can I get from this device? So with an SSD, I'm able to get around 1 Gbps bandwidth. And next scenario is PMEM, which is like doing the same test on PMEM device. I'm able to get up to 3 Gbps read bandwidth, which is like already almost 3 times higher than SSD. The SSD that I used here is very fast. That's why I'm getting more than 1 Gbps, 1.2 Gbps. That's already a very fast SSD. And compared to that, PMEM is much higher. And within this FIO workload benchmark, there is an option to run this PMEM aware setting. Using that option, I'm able to get up to 6 Gbps bandwidth from the PMEM device. That is very high compared to what SSD can give. You can see here the light blue bars are much lower compared to the green bar, which is PMEM. That's like a 6x improvement, 6 times improvement in bandwidth compared to SSD. This is the throughput. What about latency? Here I am showing again the same 3 tests: random read write, and random write. And on the y-axis, I am showing microseconds, how many microseconds it takes to do the 4 KB read. On a SSD, 4 KB read takes almost 225 microseconds. And as you go towards write, it is lower, 40 microseconds. But on a PMEM device, it's almost like 0. In fact, the actual number is 1 microsecond. Compare that to 225 microseconds. That's like a 225x improvement in latency with PMEM compared to SSD. Remember, again, this is a very fast SSD, and the PMEM that I'm talking about is like 200 times better than this very fast SSD. This is the main point of PMEM. Okay, now that we talked about raw I/O performance, how can this like high throughput and high latency and low latency translate into real workload like MySQL database or Oracle database? Now let's look at that. So here I'm showing the MySQL performance. On the y-axis, I'm showing transactions per second, which is like a throughput. On the x-axis, I have again 3 different tests: read only, read write combination, and write only. Again, I'm comparing NVMe SSD with a PMEM. So I'm normalizing everything to SSD. So if you see, this is the SSD number, and this is what I get from the PMEM. So let's say SSD is doing 1 million operations per second. The PMEM is able to do like 5.5 million operations per second. That's very high compared to the SSD. And this is a MySQL database. Similarly, latency, I'm showing latency on the y-axis, and you can see here, instead of 1 microsecond, I'm getting like 0.2, 0.18 microseconds for different tests, like read, write tests. So that is again a big improvement. It's almost like 5.5 times better throughput and latency with PMEM compared to the SSD. And remember, this is like MySQL database, which is the core component of many applications. Like even Facebook totally runs on MySQL. All your photos that you upload, everything, all the friend requests and everything is stored in database, which is like MySQL database. And these kind of improvements with PMM can drastically improve the performance of big applications like Google search or Facebook or YouTube or all those. Next, let's look at Oracle database, which is again very famous database used by all these enterprises like Flipkart and Zoom, all Indian Airlines, all the airline companies, banks, online commerce, e-commerce companies use Oracle because it's very stable and there is a lot of support from the Oracle company. So Oracle is very widely used database. In Oracle, here I am showing the throughput, comparing SSD throughput with PMM throughput, which is like on the y-axis I am showing normalized throughput. On the SSD with different configurations, I am able to get up to 1, and on PMM I can easily get like 35%, like 35% better throughput. Just by, I didn't change anything in Oracle. I just changed from SSD. I moved the database from SSD to PMM, and this is what I get, like 30% better performance from Oracle. Okay, next let's look at scale out performance. In general, scale out, the term scale out means if you have one application and your load is, one application is not able to support the customer load, like clients, a lot of clients are trying to connect to this single application. Generally, the solution that people try is run multiple instances of that application and do like distribute the load across those instances. That's called scale out. So here I have, instead of, I already showed you MySQL, how MySQL performance improved with moving from SSD to PMM. It improved by 5.5 times. Here in this example, in this scenario, I'm showing scale out performance using the same MySQL. So on the x-axis, if you notice, I'm trying different number of VMs, 1 VM, 2 VMs, 4 VMs. Same MySQL, I run in 1 virtual machine, 2 virtual machines, and 4 virtual machines. So what happens with SSD is, as I increase the number of VMs, I can get better throughput, but it's not like linear. You can see with 4 VMs, I am only able to get double the performance. It's not 4 times. Ideally, I want to see 4 VMs should get 4x performance, but because SSD is not very fast, that is becoming a bottleneck. If I run the same test on PMM, from 1 VM to 4 VMs, I can get up to 3.5 times, which is not ideal. Like ideal is like 4 VMs, 4x the performance. That's ideal. But at least on PMM, I can get up to 3.5x, which is very close to ideal. In the same test, this is how the latency is changing, going from 1 VM to 2 VM to 4 VMs. So SSD, the light blue line, if you see, even though 4 VMs, I'm getting double the performance, actually the latency is very bad. Latency is going from 1 to more than 2, around like 2.2, which is generally not acceptable. So if you run one instance, you get 1 microsecond latency. And if you run 4 instances, each instance is getting up 2.2 microsecond latency. In many applications, that's not acceptable. For the same test, when I run on PMM, the latency is same. Even if I run 1 VM or 4 VMs, it's only increasing slightly. From 1, it changed to 1.2. It's not becoming double like in SSD case. So this is like 20% increase is generally acceptable, but double is generally not acceptable in any big application. So that's how PMM can help in your scale out scenario. And finally, let's look at some PMM aware applications, which are like some of the applications. For example, Microsoft released a new version of SQL database. It's called SQL Server, which has PMM support. That means they changed their application, they modified their application to understand PMM semantics and take advantage of that PMM. So here I'm showing the SQL Server performance. On the y-axis, it's again throughput. Higher is better. So better throughput is always desired. So NVMe SSD, let's say normalized to 1. I tried different combinations of PMM and I can get up to 1.16 times, which is like 16%. But this modified, when I tried the modified application, I can get up to 1.22, which is like a 22% improvement in throughput. So Microsoft changed their SQL Server application to understand PMM. And with that change, we are able to get almost like 22% more improvement, 22% improvement on top of SSD. Without that change, the best case is 16%. So by changing your application, you can generally get more throughput from the PMM. Now, the other application that is changed is Redis, Redis is a high performance in-memory key value store. So it's a database, but everything sits in memory. It doesn't write into SSD. It doesn't read from SSD. So it's very high speed, high performance database. But like I said, because everything is in memory, if you power off the system, it goes away. That's the basic Redis. That's called vanilla Redis. It uses both DRAM and SSD. Every time you start Redis server, it reads the database from SSD to DRAM, and anytime you get a request from the client, all the requests are served from the DRAM. That's vanilla Redis. Typically, it is used as a caching layer in a large application. So what we did is in VMware, we modified Redis because it's an open source database. Anyone can download the source code and modify the code and try different changes. What we did in VMware is we modified Redis application to understand the PMM, new PMM technology. And with that, what advantage we get is we get better throughput and latency. I'll show in the next slide how much better it is. And we get also instant startup and recovery. So like I said, when you start Redis, it reads the whole database from SSD to DRAM. That will take some time. But in the PMM aware Redis, you don't have to read it. There is no DRAM or SSD involved. It only reads and writes from the PMM. So there is nothing like it is loading from SSD to DRAM. There is instant recovery or instant startup. I'll show all those results in the next slides. So first, let's look at throughput. Here I'm showing operations per second with 3 different tests: read only, read write, and write only test. And 3 different scenarios. One is NVMe SSD, second one is regular PMM, and the third one, light green one, is PMM aware Redis. So with the regular PMM, I can get in the write only test, I can get up to 1.4x throughput, better throughput. But with the PMM aware Redis, I can get up to like 2.4x improvement in the write only test compared to SSD. That's a big improvement with the PMM aware Redis. Next, latency, similar story. Like latency in these 3 different scenarios. With the NVMe SSD, it's 1 and with the PMM, we get like 0.2 latency compared to 1 for the write-only test. And with PMM aware, I can get even lower, like 0.6 or something, which is like 12x improvement in latency with the PMM aware Redis compared to SSD. So you can see the difference between PMM and PMM aware here. If you don't change your application, just remove the SSD and replace with PMM, you can get up to 8x improvement. But if you change your application and use the same PMM hardware, you can get even more performance improvement up to 12x. That's the difference here. And I talked about this instant startup and recovery. So I have a 128 GB database, and when I start the Redis server process, it reads from the SSD and it takes 242 seconds to start. But if I start the Redis server from pmem, it reads everything from pmem to DRAM, and that even that takes 83 seconds. That's a 3x improvement, but still it is taking 83 seconds. But the pmem aware Redis that we created in VMware, it's an instant startup. There is nothing to read. It puts everything on pmem last time when it shut off. So when you start up, it has everything on the pmem. So main message from this two scenarios, SQL Server and Redis, is application changes may be needed to maximize the performance using pmem. So like I said in both examples, just by changing from hard disk to pmem, you can get some advantage, but to get the best performance, you need to change your application to understand this pmem and take new advantage of this new pmem semantics. So to conclude, pmem gives up to like 5.5x improvement in database micro benchmarks and up to 35% improvement in enterprise class applications like Oracle and MySQL. I showed up to 35% improvement. And scaling out VMs, like scaling our number of VMs, increasing the number of VMs on pmem can take full advantage of the device bandwidth. Instead of running one application, if you run 4 applications, you can get the same latency, but much better throughput. And modifying the application code can get maximum pmem benefits, even better than just changing pmem and with SSD. Finally, we wrote 2 white papers on this topic, and they are available for anyone to read. Those papers have more details about the pmem and all the experiments we did and how you can take advantage of this pmem in your system. The links are provided here in the presentation. That's all from my side. If you have any questions, I can answer.
It's very interesting presentation, Praveen. Very well structured and informative and interestingly presented. Any questions? The participants can ask your questions.
No, ma'am. No questions, ma'am. It was clearly explained.
Yeah. So if no questions, the final thing you just need to remember is pmem is like a combination of both memory and storage. It takes the good things from memory.
Praveen, there is a question from Professor Valli Kumari.
Okay.
She's asking, does Windows, in the chat box, the question is there. Does Windows support this?
Yeah,
And
I showed you. Here I am showing a screenshot from Windows. So if you boot Windows on a system with pmem, it will show up in Disk Manager as a new disk.
Okay.
You can right click on the disk and do format and use it for your application, like games or database or movies or whatever. You can put data on that disk and it will be very fast.
Okay. And are there any page replacement algorithms? This is also an extension of that question.
Like I said, in the app direct mode, it's all managed by software. So user is supposed to write the data and read the data. Means you issue commands to read data, write data into pmem. But in memory mode, hardware does all the page replacement.
Okay.
Hardware is moving data between DRAM and PMEM, so their page replacement policies will be done by hardware.
There is one more question. Can we use them in the current 11th generation PCs, or do they require sophisticated devices?
11th generation Intel processor, like here, 11th
Hello.
generation Intel. Yeah.
Hello.
Hello.
You're audible.
Yeah. Like here, I'm showing example of 11th generation, right? We can use it in
Yeah.
11th generation. Yeah. Generally, the thing is, this PMEM, they don't sell PMEM for laptops. They sell only for servers.
Okay.
But the same 11th generation processor in server can support PMEM.
Okay. Any other questions? He is the right person to answer all possible questions around this particular topic. You can feel free to ask appropriate questions, of course. There is one more question, sir. Is this PMEM similar to unified memory architecture, which is being used by companies like Apple?
There is a slight difference between this and that. The concept of unified memory is, in the example I'm showing here, this Inspiron laptop, Dell laptop, there is this Intel graphics card, right? So in general, in this graphics card has its own memory, and processor has its own memory. Here 16 GB, what is shown is processor memory. So the graphics card generally has its own memory, like 2 GB or something, its own memory. So unified memory, the concept is, instead of having separate memory for graphics, the graphics card can access the same system 16 GB memory. That is unified memory concept. That is different from PMEM.
Yes.
There is single memory. In the unified memory concept, in the laptop, Apple laptop, there is single memory. There is no separate graphics memory. That is actually a good thing, because now if you want to do some graphics processing, it has to move the data from this 16 GB system memory to the separate 2 GB graphics memory. So in the unified memory system, there is no data copying from one place to another place. Graphics card can directly access CPU memory.
Okay. Praveen, one more question from Professor Vali Kumari. Can Redis be used for blockchain data structures or has predefined data structures?
Redis is a very generic database. So you can define your own data structures. There are no predefined. There are basic structures like list and stack, kind of predefined structures, but you can definitely define your own data structures in Redis. You can store whatever data you want. You can store a string. You can store a list in the database. It's not like relational database. You can store whatever data type you want. There is no concept of tables and all.
Yeah.
Like relational database, this is like a key value store. The value can be any type. It can be blockchain data structure, or it can be string, or it can be number, any type.
Okay. Any other questions? Okay.
Vigneswari Geetika raised a hand.
Hello, sir.
Yeah.
Yeah.
Good morning, sir. Good morning, ma'am.
Yeah, you can ask your question. You can come in.
Sir, I have a small doubt regarding general basic structure, sir. Actually, sir, you showed us that memory pyramid, no, sir.
Yeah.
Sir, in that the fastest memory will be communicating with the CPUs.
Yeah.
In this cache memory and DRAM directly communicates with the CPU. And secondary storage like SSD and hard disk, they are indirectly communicating with CPU via DMA controller, no, sir. But then why again persistent memory?
Because it is slow. Like anything you want to read from SSD, you have to first put into memory through DMA. What DMA does is it moves the data from a storage SSD to memory, and then CPU can read it. Basically, CPU can only read anything from memory. It can't directly read from SSD. So when you ask for something in the SSD, DMA will move that data from SSD to memory, and then CPU can read it. So with this persistent memory, CPU can directly read it. It doesn't need DMA, it doesn't need anything.
Okay. Sir, then can we say that persistent memory has some information from like flash SSD and all?
It is similar to flash SSD. Yeah. From the software side, it looks like flash SSD. Like I showed in the Linux example, or this one in the Windows example. It just looks like a disk SSD. Persistent memory looks like a SSD, at least in the app direct mode. You don't see any difference between functionally. It's the same as SSD. EMM is same as SSD, just that it is very fast. It's like 5 to 6 times faster than any SSD that you can buy.
Okay, sir. Thank you, sir. Thank you for your information.
No problem. Yeah.
Any others wants to clear their doubts? Okay, thank you, Praveen. Now over to Mary Saujanya. Saujanya?
Thank you so much, sir, for accepting our request at a very short notice. I thank today's speaker, Mr. Praveen Kumar, for his excellent talk on persistent memory, for providing us a brief introduction on different persistent memory modes and different types of persistent memories, memory mode use cases, scenarios, app direct use cases, etc., and also for answering the questions also patiently. I thank our principal, Professor P. Srinivasa Rao Garu, Professor S. Vijayananda Rao Garu, Head Department of ITCA, Professor Kunjam Nageshwar Rao Garu, Head Department of CSSE, the Director and Technical Staff, Computer Center, for all their support, and all the participants and faculty who have attended the session. Thank you, one and all.
Thank you.
Thank you, Praveen.
Yeah.
Now we can.
Now all of you can leave the meeting. Thank you.
Thank you, ma'am.
You're welcome. Hope you have gained some insights on a very good topic, that is persistent memories.